Welcome to Samsung Next Meets. Today, my guest is Jonas Bylander, a quantum computing expert from Sweden.
I'm on the faculty at Chalmers University of Technology in Gothenburg in Sweden. I'm heading up the experimental quantum computing team here at the Wallenberg Center for Quantum Technology. So we have a 10-year funding from a foundation for building a quantum computer here at the university. My background is in physics, so I've been doing superconducting quantum circuits for about 12 years now. My team is building a full-stack quantum computer. So we're focusing, of course, on the hardware, the quantum hardware, the control methods, and the firmware for this quantum processor, and also on some intermediate layers of. So we're building full stack, and we're getting some things off the shelf, but most things have to be dealt with, interfaced, built. Also, very importantly, we have a great theory team here that we work with, and the collaborators in Europe, and also some companies as partners. So we are adapting use case applications, problems that could be interesting for these partners that we are mapping onto the quantum computer and trying to solve. That's what I'm doing. Ultimately, all matter is quantum, behaves according to quantum mechanics. We just don't see it in our everyday lives, but we have developed some technology to control electronic devices. That's what we're doing here. So we can manipulate the quantum properties of these quantum devices, and then we can encode information into these devices. And normally in a regular computer, of course, we encode zeros and ones, but in a quantum computer, we can put these zeros and ones in a superposition. So it's the state of the quantum bit is a little bit of zero and a little bit of one at the same time. And then we can do computation on these two states at the same time in parallel. And then we put many qubits together. So with 2 qubits, we can put 4 states in superposition. So we have 4 states at the same time. With 3 qubits, we have 8, and so on. So it becomes very parallel, very fast. And then for some problems, you can devise an algorithm to solve it much, much more efficiently than you could on any regular computer. So a quantum computer with many qubits, well, not so many qubits, could outperform even the best supercomputer. That's the idea. I must add, though, it's very, very hard to control these circuits. That's why we don't have quantum computers yet, because during the computation, there are always errors happening, and we have to control those errors without destroying the quantumness of the quantum computer. So that's something we work on a lot to make them work better. Because some computational problems that a quantum computer can solve cannot be solved on a regular supercomputer. And we're still figuring out exactly which classes of problems, which problems a quantum computer can solve. And it seems clear, though, that there are some advantages in, for example, in chemistry and we say quantum chemistry, calculating the energy levels of molecules. That's interesting for example, for pharmaceutical companies. And then optimization problems appear everywhere in engineering or applied math. There's some potential killer apps there if we can just make a few more qubits that work really, really well. I think it will take more than 5 years. I'm just saying more than 5 years because I don't know when. And I think maybe in chemistry, calculating some properties of molecules or materials that could be industrially relevant, I think is probably where it's going to happen, or that's where it could happen first. Yeah. So it's not something for everyday use for ordinary people, but it could be of big industrial interest, I think. There's some universities and big companies and startups that have great activities going on, but I think of a hub as a kind of an ecosystem where you have moving parts and ideas flowing more or less openly. So in that sense, like what's going on in Europe with the European Commission's flagship on quantum technologies is it's a distributed hub, let's say, all across Europe. But I think that's really exciting. Compared to the US, I think what's happening in the EU is important now. There's a push to develop open access and open source platforms for quantum computer, not just things that are locked into big companies. Do we have an edge? I think that there's going to be a lot coming out of that environment. And there's definitely a need for research on several different platforms too. We can't decide yet what's the winning platform or software or hardware that's going to win. So we have to do different things. And I think Europe is in a good position there. Because I'm a physicist, quantum physicist, I would pick someone I admire from our field, and the people that were really contributing in the very beginning, making superconducting qubits and understanding how they work, was a team in Saclay in France, outside of Paris. The whole team at the CEA in Saclay. Those are my scientific heroes as a PhD student. Well, you got me there.
Yes, like it.
I mean, I think autonomous vehicles would be really cool. Some people working in the field are telling me that that's as hard as quantum computing to make it really work, so they could drive everywhere safely, because I think the safety there is a big issue.